Getting reliable results requires a complete shift in mindset. You have to stop talking to the AI like it's a human colleague and start programming it like a compiler. The days of typing, "Please write me a blog post," are over. Securing predictable, high-quality outputs from generative AI is an engineering discipline, requiring strict syntax and structural control. Large language models, or LLMs, do not actually understand the text they read. They are massive statistical engines designed to do exactly one thing: predict the next most likely word in a sequence. Vague instructions force models to guess, generating millions of branching probability paths. We fix this using in-context learning. By assigning hard constraints, you aggressively prune unwanted probabilities. Few-shot prompting adds exact examples, locking the prediction engine and forcing it down a single, precise output path. By layering these rules, examples, and negative constraints, you remove the model's ability to drift. You dictate the tone, the exact formatting, and the logical boundaries it cannot cross. This specific context acts as mathematical scaffolding for the prediction engine, anchoring it to reality and preventing hallucinations. Even with strict formatting, some problems are too complex for a model to solve in a single, continuous generation. Tasks involving heavy math or code execution require the system to perform rigorous analysis rather than basic pattern matching. Chain-of-thought prompting commands the model to reason through a problem step by step, processing each variable sequentially instead of rushing. For even harder problems, the Tree of Thoughts framework allows an AI to simultaneously explore multiple reasoning paths, evaluate success, and discard the incorrect ones. This kind of cognitive scaffolding forces the model to double-check its own assumptions. It actively prevents the system from wandering down logical dead ends and creates a transparent, verifiable trail of how it reached its conclusion. Writing effective instructions at this level is about designing the actual cognitive architecture the artificial intelligence must follow to process information. Manually writing and tweaking these intricate instructions is incredibly difficult to scale. The real frontier of this technology abandons isolated text prompts entirely in favor of system-level orchestration. One piece of that orchestration is Retrieval Augmented Generation, or RAG. It's an architecture that links a language model to a live external database, allowing it to pull factual, up-to-date information before it generates a response. A framework called DSPY, originating from Stanford University, treats language models like optimizable mathematical functions rather than conversational agents. Instead of a human guessing which specific words will produce the best result, DSPY automates the entire process. You feed the system a dataset of desired inputs and outputs, and the framework automatically tests, evaluates, and rewrites its own internal prompts to maximize accuracy. Engineering an AI system is now an automated, data-driven software development lifecycle where the machine optimizes its own instructions. When you combine structured constraints, external database connections, and self-correcting logic, you get a fully autonomous AI agent capable of executing complex, multi-step workflows without human intervention. A sharp divide is forming in the market right now. On one side are organizations building robust, agentic systems that scale predictably. On the other are companies attempting to build products on top of fragile, inconsistent chat interfaces. Continuing to rely on unstructured inputs and hoping for the best guarantees broken workflows when these models are deployed in real-world production environments. Building secure, enterprise-grade AI requires engineering-led architecture. To establish a system capable of surviving a production environment, contact Jay Carter at bearstandingtall.com.